Hello guys, this is your virtual lesson 4 for chapter 11. You are going to need your lesson 4 that we started on block day, either Wednesday or the yesterday. Oscar's just there, to help me out here. Hello guys, we miss you. I know that we started lesson 4, but we didn't really finish because we were talking about homogeneity, but we never made it to association and independence for chi-square. So I'm going to teach you the rest of this lesson 4. There are some things that you will need before we get started. You will need pen, yeah. I did 2 different color pens. That's probably going to help you. A highlighter and calculator. Of course, you always need your calculator, right, Oscar? Yes, okay. Fantabulous. Okay, so we finished up to here. This is an example, and we didn't do the example yesterday. So if you could do me a favor and pause this video right now, I need you to work through this example. So go ahead and read through this example. You don't have to do the entire test here. I would like you to do a ho and a ha, write your hypotheses, check your large sample size, so make sure you get all of your expected counts. Remember, you get that from the calculator. Taught it to you yesterday or Wednesday. Get out your percolator, that'll help you. You need your chi-squared and your p-value. df, remembers from up there. Write a conclusion. So pause this video right now. Go see if you can do that. Try your best. Dun, 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 dun. You pause the video. Yes, you're a good student. Yes. Right, Oscar? Good students. Ms. Chove has fabulous students. We're just assuming the best. Okay, fantastic. They paused the video, and they came back with all of their answers. So, here's some answers. Your ho. The thing we're trying to disprove is that there is no difference in the distribution. There's no difference in the distribution. And we are looking at the distribution of birthdays for people born before 1980 and after 93. Interesting. Okay, and we're trying to prove that there is a difference. So I want to disprove the no and prove that there is a difference in the distribution of B-days for people born before 1980 and after 93. I just did little hoopy-doopy, what are those called, quote things? Air quotes? No. Repeat things. Okay, and my large sample size I need to get from the calculator. So here's what I did, little trick. I plugged in my data into my matrix here. I edited my matrix A, there it is, and then you do your stat tests, and by golly, after you do your stat tests, you get your chi-square p-value. Your matrix B gets populated, so let's go find our expected counts in our matrix B. Here's my matrix B. Ooh, those are my expected numbers. So what I do, instead of like having to rewrite an entire table, is I do this, guys. There's a table, there's my expected counts, and I put all these numbers right there in the table. So that's another way to do it if you have room in the table and if you can see the difference. You also need to make sure that you label them, okay? That's one way to do all your expected counts. For a large sample size, I said C above in the red, and they're all at least 5, so we're good. My smallest one's 8. And from the calculator, from our test, we did get a chi-square. This is actually interesting because the p-value is pretty big here. There's my chi-square and my p-value. Also make sure to make a note to yourself. The df is the number of rows we have -1 times the number of columns we have -1. So this is a 7 by 2, so I take my 7 by 2, subtract 1 from each one of those, so I have a 6 times 1, df is 6. Holy moly, Oscar. Calculator says the same thing. Interesting. Okay. Okay. 7.09 is my chi-square. So, do I reject the whole? Do I reject the whole? Well, is P low? I don't know. Maybe we should ask the reject the whole guys. You want me to play it? Well, this is kind of a weird part of the song. It's when he kind of looks snaky. But, yeah. There we go. Okay. Wish I was here, huh? Woo! Okay. I'm back. So that one P is low. We reject the home. No rejecting home. Okay. Since p-value is 0.31, definitely greater than alpha, I fail to reject the hoe, and I cannot conclude that there is a difference. All right, that was fun. Cool beans. Let's move on. So we're going to move on for a chi-square test for association and independence. That's the rest of the lesson. It's pretty much the same as homogeneity. Calculator stuff will pretty much be the same. So what does it mean if two variables have an association? What does it mean if two variables are, I should have highlighted that one too. I have so many different color highlighters going on. Actually, can I use my yellow one? Independent. You know, it's kind of hard to hold the phone and write. I don't know how it's going to work. So if two variables are independent, two variables are independent, then the values of one variable do not tend to occur in common with the other, aka they affect each other. Oops, I skipped. If two variables have an association, whoopsie-doodle-poodle, there is a relationship between the two variables. That's what we're looking at in this next section. Here we go, page 2 of lesson 4. Looks like this. So, how is a test of association and independence different than homogeneity? And to be honest, it's really not that much different. But in a test of homogeneity, we are comparing the distribution of one categorical variable in two or more populations or groups. In a test for association or independence, we are investigating the relationship between two categorical variables across one population. So a little bit different. The basic idea is pretty much the same though. So our null hypothesis, our null hypothesis, is that there is no association. That's what I'm trying to disprove. And my your alternative hypothesis, is that there is an association. That's what I'm trying to prove. Very, very similar to homogeneity. Expected counts are the same as homogeneity. Your expected counts are equal to the whole ordeal we did yesterday. With the, on top, we have the row total multiplied by the column total, and we divide that whole thing by the table total. And that's if you really need to get like one specific term, but remember the calculator just pops out the answer for you. The conditions, OMG, are the same. We have random, large sample size, and independence. Same that we do for goodness of fit, and also the same for homogeneity. Same. We're gonna do an example now. We did this, what did I say? Chapter 5. Chapter 5, Oscar? Chapter 5, Oscar. I didn't have you in chapter 5. No, you came around. All right, laughter. Anyways, we looked at the relationship between gender and having allergies for a random sample of 40 students who completed the Census at School survey. It's talking about whether or not they had allergies. So let's see, we've got female, male, allergies, no allergies. Interesting. In chapter 5, we concluded that female and allergies were not independent. Okay, interesting. For the people in this sample. Calculate appropriate conditional distributions to verify that this is true. And then we'll get to the proof with the chi-squared. So this is interesting because we did this in chapter 5. And we're also going to do it now and see if what we get matches with different statistics. So female and allergies, we say are not independent. So we're saying being female makes you either more likely to have allergies or less likely to have allergies. So here's what we do. We've got for females, we want to prove that the probability of having allergies, given that we're female, so being a female doesn't have any effect on having allergies, and we'll check this one first. So let's see. Out of all, this says, out of all the females, how many have allergies? Out of all the females, how many have allergies? Out of all the females, 23 females. So out of the 23 females, how many have allergies? Out of the 23, 10 have allergies. 10 out of 23. Should have left more room. Where can I put an answer? I guess I have to put it down here. I get 0.43. So that is out of all the females, how many have allergies? If this is independent, I would have to check that that is equal to just the probability of having allergies. So being a female, does that have any effect on the allergy portion of that? So the total amount who have allergies are total amount of the allergies is 10 plus 8 is 18. So we've got 18 people out of how many of the total? 40. So out of all 40 of my people, 18 have allergies. So 18 out of the 40 is 0.45. So it actually looks like being female, you're less likely to have allergies than just allergies in general. So there we go. I just proved that being female, you're less likely to have allergies. Interesting, interesting. So I would hope that in part B with my chapter 11 stuff, it's gonna match. I pretty much just proved, well not proved, that these aren't independent, and that's what my chi-square is also gonna test. So do these data provide convincing evidence? Okay, so do these data provide convincing evidence? So get out little Miss Highlighter here. That says a significance test of an association. Association. That means chi-square. Between gender and having allergies for the population of U.S. high school students who filled out this survey. Okay. So, I don't know about you, but I'm kind of tired. It's actually Thursday after school. And I really want to go home, guys. It's kind of late. I don't know if you can see the clock, but it's almost 5 o'clock and I'm still talking. Okay, Oscar wants to go. Okay, stop talking now because I'm just rambling now. It's been 14 minutes on this video. Can you hear me? I don't know if you can hear me. I think it might just be, okay. So we're not going to do the whole test. Let's just do the difficult parts of the test. If that's okay with you, let's do what we did on the previous side with the hoe and the hop, large sample size, conclusion, yada yada. So the hoe is that there is no association between our two variables. There is no association between gender and allergies. and the ha. What we're trying to prove is that there is an association. That's what it says. Is there convincing evidence that there is an association? So ha, there is an association between gender and allergies. Okay, so trying to prove that there is an association. Cool beans. So next thing is that all of our expected counts are at least how big? 5, Mr. 5. Okay, fantastic. Large sample size. So I think I need to plug this into a calculator because here is my table. Leave out the totals, so it's really just 2 columns and 2 rows. So that's still enough to use the calculator. I don't have to do that by hand. So let's see, I'm gonna go second, x to -1. Let's go edit a new matrix. And I want a 2 by 2. This is 10, 8, oops, 8, 13, and 9. And now if I stat test chi-square, oh, notice that. Stat test chi-square, we have goodness of fit, but then it's the same chi-square for homogeneity and independence, this test here. Interesting, huh? You don't care. Great, same. Because we got to put it into a matrix because there's more than one variable going on. So there's my chi-square. Whoa, small chi-square. Interesting. P-value, holy moly, that's a very big p-value. Weird, we don't normally have p-values that big. DF is 1 because it's a 2 by 2. So we got 1 times 1, which is 1. Interessante. Okay, what am I doing? Large sample size. Come back. Let's go back into our matrix and let's go find our matrix B. There are all of my expected counts. Sweet. So I'm going to use this. I want to write these down. Again, you can either put it in your table. I'm afraid I won't be able to write that small this time. So what you can do is you can just make a little quick matrix or a little quick table. It's just a 2 by 2, so honestly I could just do this, guys. And I could do 10.35, 7.65, 12.65, 9.35. Expected counts are all at least 5, so we're good. Let me just write that down. All greater than or equal to 5. Sweet, we're good. So now I can calculate what I already did. I don't know if I did this in the last problem, but what's good to get in the habit of, shooby-dooby, I should have done it. Darn, it's writing out my terms. We did this for goodness of it. So what we should do is take observed minus expected. So let's say for female with allergies, that's our first term. We observed 10. Remember all of this right here, what was given to us is observed counts. So this 10 is my observed. I expected 10.35. So I expected a little bit more. Actually, I got less than I expected. Next one is 13 down here. Observed, 12.65 expected. That's not that much off, is it? It's not even one person off. Same with 8 and 7.65. Same with 9 and 9.35. That's why our p-value is so high. This isn't very strong evidence. None of these are more than 1 off, to be real. So I don't know. Okay. So back to chi-square. So writing out the actual term, we need to take observed minus expected. So the first one is 10. I expected 10.35. Square it, divide by expected. That's the formula for chi-square plus dotty because I'm lazy. Last one, let's do the 9. 9 minus 9.35 square divided by 9.35. And then you can pop back over to calculator and say, hey, calculator, what did I get in that chi-square test? And you can just pop in the answer. That's weird. That's like our alpha. 0.05, but that's not what I'm comparing to my alpha. I'm comparing that big old p-value to me alpha. Okay, whoops. So now my conclusion, I write since, okay, my writing's getting all weird. P equals 0.82, which is definitely greater than an alpha. We usually use 0.05. Should I ask them? Should I ask them? Should I ask them? Are you annoyed? Let's rewind it. Just a couple sentences. Oh, there it is.
No, you reject that hoe. That one P is no, you reject that hoe. That one P is no, you reject that hoe.
Oh, it's after 5 now. Oh, I better get going. Okay. Oh, shooby-doo. Do. P's not low, so I fail to reject hoe and do not have convincing evidence of my is that there's an association. Convincing evidence of an association. Oh dear. Association between gender and allergies. Okay, you could write it out on your paper. Maybe you have room. Between gender and allergies. Okay, hopefully that didn't take the whole period. This is 20 minutes. I'm not exactly sure what I'm going to have you guys do next. Thanks for listening. I'll go think about what else to plan for you guys. Say bye, Oscar. Thanks for listening. Hopefully it's just you guys on this YouTube video and it's not like other people scouring the internet. That'd be weird if they're listening to my video because, you know. All right, guys. Have a good weekend.